Calculus, Unit 7, Day 64. Our objective is to do some more work with volumes of solids of revolution, and now to find volumes of solids of known cross-sections. So volumes of solids with known cross-sections. Calculus can not only be used to find the volumes of solids created by revolving two-dimensional shapes around an axis, which are going to give you circles, but also the volumes of solids formed by cross-sections that are geometric shapes. So in this lesson, you will derive the formulas for finding volumes of solids, given that their cross-sections are either squares, isosceles right triangles, equilateral triangles, and semicircles. Okay, I think these pictures here are actually pretty good, and I want to just talk about squares, isosceles right triangles, equilateral triangles, and semicircles in a second here. So everyone knows a square is going to have four sides of equal length, and the area is just going to be side times side, length times width, whatever, but it's going to be x times x, which is x squared. So how does that help us for what we're working on now? Well, I'm taking a look, I'm going to rotate it around this x-axis right here, this function f of x, which is the top, so that's the outer function, and then we have this g of x, which is the lower function. Well, the distance between those two is whatever the value of f of x was minus the value of g of x. So this one side, whatever side you want to look at, is f of x minus g of x. So if it's a square, then that means both sides are going to be the same. So we want to start filling in some stuff. So let's find the area of the above square. So let's do. So we find out the area's length times width, or side times side, which is just going to be f of x minus g of x all squared. So when I'm trying to find the volume, similar to what we just did in the last section, I'm now trying to find the volume from point A to point B, and it's going to be the sum of all these areas of these squares, f of x minus g of x, and then times the height, which we just used the dx as the height. Okay, so this is what we're going to use for all the problems dealing with a square. Alright, so let's come back here. We're going to look at an isosceles right triangle. So if I have a square and I draw this diagonal, then hey, what's the area of just this triangle? And that's a right angle. That's why I built it within the square. So it's going to be 1/2 base times height, which is just 1/2 x squared. So very similar to what we just did. So now, again, I have my f of x is the top function, g of x is the bottom function, here's the x-axis. So the distance between the two functions is f of x minus g of gx, f of x minus gx, and it's going to be those two multiplied together. So what's the area of that triangle? Let's write that down. And we notice 1/2 base times height, or side times side, because it's an isosceles right triangle based off a square, and so that's 1/2 f of x minus g of x. So now if I know that all the cross-section areas were added up, the total would be the volume of the solid pictured. So how do we write this in calculus using an integral? So they have a little piece of paper here, whether it's a square or an isosceles right triangle, just picture there be an infinite number of isosceles right triangles, or an infinite number of squares. So that is the volume. So in this case, it's going to be the integral, and I'm going to bring the 1/2 out, and because it's 1/2 base times height, or side times side in this case, and now it's going to be f of x minus g of x all squared dx. So it's the same thing as what we got for the squares, except it's half of that. And again, you can start with the half inside and then pull it out, but that's what we're going to end up with, right? So next we're going to look at an equilateral triangle, and then we're going to look at semicircles. Well, for an equilateral triangle, all three sides are the same. So how do I find the area of this? Oh, I got to go through, and I got to take this, and this was a 60-degree angle, this, so it becomes a 30, 60, 90. So what I end up finding out is, oh, this ends up being half of the original side. And now I have this 30, 60, 90 triangle with this being 1/2 x, this being x, and then this side ends up being square root of 3 x over 2, because it's always square root of 3 times the smallest side. So this will help us come up with a way to find the area of a triangle given that the sides are f of x minus g of x. So there's our original function, there's g of x going down below, and there's my x-axis. So my outer function is my f of x. So what am I going to do? And let's kind of draw this some things in. So I know all three sides are the same. Again, I know this is a 60-degree angle because I drew the altitude, which makes that a 30-degree angle. So this side right here is going to be half of f of x minus g of x. And then this altitude or height right here, because it's 1/2 the base times the height, this is going to end up being square root of 3 times that smallest side opposite 30-degree angle, which I just found was 1/2 f of x minus g of x. So now I can use this information to come up with the way to get the area. So when we look at the equilateral triangle, area of any triangle is 1/2 base times height. So there's 1/2, there's the whole base, f of x minus g of x, or we can look at it as 1/2 base right here, times the height. And what is the height? That's the square root of 3 times 1/2, which is square root of 3 over 2, times f of x minus g of x. So now let's simplify this. So the area of all equilateral triangles is going to be square root of 3 over 4 times f of x minus g of x all squared. So now when they want to know what the volume is, hey, we're just going to say the volume is square root of 3 over 4 of the integral from a to b of fx minus g of x all squared dx. And you start to notice, like, oh, they're all fx minus g of x squared. The square has no constant out in front of the integral. We found out that the isosceles triangle had 1/2, and now this is square root of 3 over 4. So every single equilateral triangle will have that square root of 3 over out in front. So if you get rid of that square root of 3 over 4, then it's just the cross sections of a square. Okay, but this is if all cross-sectional areas were added up, the total would be the volume of the solid pictures. How do we write this in calculus using an integral? And this is what we would get. Okay, so let's now do the last one with semicircles. Okay, and what we're starting with is that the distance between the two functions are always f of x minus g of x. So that's the diameter. So this little amount right here is half of that. So the radius equals 1/2 f of x minus g of x. Okay, and then we know that the area of a circle is 1/2 pi r squared, but our radius is also 1/2. So let's go and take a look at that. So let me mark this up. And as we just said, it's 1/2 pi r squared and 1/2 pi, and my radius is 1/2 of f of x minus g of x, minus, and all of that squared. So 1/2 squared is 1/4, times 1/2 is 1/8. So actually, let me write this up the long way. So we get 1/2 pi times 1/4, and then we get our f of x minus g of x. Now that's squared because I squared the 1/2, and then I squared this. And now I can write this as 1/2 times 1/4 is 1/8 times pi, so 1 pi over 8, and then f of x minus g of x all squared. And so how does that help us find the volume if all the cross sections are all semicircles? Well, volume equals, take the constant out front, pi over 8, the integral from a to b of, because that's That's 1/2 pi, and again, our radius was just 1/2, so that takes out the constant. And now we're left with f of x minus g of x all squared dx. So we should notice that all four of these have the same inside the integral, and it's just three of them have the constant that's a little bit different. So here was, when we get a square, write that down here. Again, f of x minus g of x all squared. This is when we had our isosceles right triangle. Right triangle. Okay. Down here, this is when we had our equilateral triangle. And this is when we had our semicircle. Okay, and this is how we find the cross sections that are one of those four shapes. All right, and then on section part 2, we'll do some practice problems.